All right, let's tackle one of the most common and honestly, one of the most interesting questions in chemistry. You've seen it in the lab, a reaction starts bubbling away, things are happening, and then it just stops. And I don't mean it runs out of stuff, it just seems to quit halfway through. Why does it happen? Well, to get to the bottom of it, we're going to start with a fantastic real world puzzle. Now, this isn't just some clever saying. This is a fundamental fact of thermodynamics. Under the normal conditions we live in, standard temperature and pressure, the universe itself says that the carbon atoms locked up in a diamond would be way more stable, way more comfortable if they just rearranged themselves into plain old graphite. Pencil lead. I mean, think about it. If nature is constantly pushing for graphite, why hasn't every diamond ring and necklace on the planet just poofed into a pile of great dust? This isn't just a party trick question. The answer cuts right to the heart of why chemical reactions work the way they do. It's a beautiful paradox. To solve this paradox, we need to understand that every single chemical reaction is controlled by two different forces. Think of them as two managers giving orders, and sometimes those orders conflict. These two controls decide if a reaction will even happen, and if it does, how fast it'll get there. And those two managers are thermodynamics and kinetics. The easiest way I found to remember them is like this. Thermodynamics only cares about the destination. It asks, is the finish line worth going to? Meanwhile, kinetics is all about the journey. It asks, yeah, but how hard is it to actually get there? So let's start with thermodynamics. This is all about the overall change in energy and stability. We measure this with something called Gibbs free energy, or delta G. The best analogy is a ball on a hill. Thermodynamics doesn't care about any bumps along the way. It only asks one question. Is the final destination, overall, downhill from where we started? And what decides if it's downhill? It boils down to three main things. First, enthalpy, which is basically the heat change. Then there's entropy, which is a measure of disorder, and let's be real, the universe loves a bit of chaos. And finally, temperature, which kind of acts like a volume knob for how important that disorder is. You mix those three together, and you get your answer, delta G. Okay, here's the key rule. If that final delta G value is negative, it means the trip is downhill. The reaction is thermodynamically favorable. If it's positive, the trip is uphill. It's unfavorable. So what about our diamond turning into graphite? Well, its delta G is negative. It is a downhill trip, which just brings us right back to our original puzzle, doesn't it? If the destination is downhill, why isn't the ball rolling? Well, this is where our second manager, kinetics, steps in and says, not so fast. Just because a place is downhill doesn't mean you can just slide there. See, kinetics is all about something called activation energy. This is the hurdle, the energy barrier you have to overcome to get the reaction started. Even if you're going to a valley, you might have to climb a pretty big mountain first just to get out of the valley you're already in. And boom, that solves the diamond mystery. To break those super strong, perfectly arranged bonds in a diamond requires a colossal amount of energy. The mountain you have to climb is huge. So even though the destination, graphite, is more stable, the journey is kinetically blocked. The reaction happens so mind-bogglingly slowly that you'll never, ever see it. Your diamond is safe. Okay, problem solved, right? Well, for the diamond, yes. But that only explains why some favorable reactions are super slow. It doesn't explain our original problem, a fast reaction, one with a small energy mountain, that gets going just fine and then grinds to a halt before it's finished. That's a whole different ballgame. To understand this, we have to get really clear on a critical distinction. That favorability we were talking about, that delta G, we often learn about it under perfect, idealized lab conditions. But the real world is messy. It's almost never ideal. Now, this is a point where a lot of my students get tripped up, so let's focus here. There are actually two types of delta G. There's delta G with a little circle. We call it delta G naught. Think of this as the reaction's potential on paper, its blueprint under perfect conditions. But then there's the plain delta G, no circle. That tells you what's actually happening in your beaker, right now, under its current real-world conditions. One is the blueprint of what could happen. The other is the reality of what is happening. That distinction is everything. So if the reaction's real-time favorability depends on its current situation, how does it know what that situation is? How does it keep track? The answer is a concept called the reaction quotient. Just think of Q as a progress report. It's a snapshot in time. At any second, we can measure the ratio of how much product we've made compared to how much reactant we have left. That simple ratio is Q. It just tells us where are we right now on this journey. And this is the magic equation that connects the blueprint to reality. Now, don't get hung up on the math. Focus on the big idea here. The actual real-time favorability, plain old delta G, depends on both the built-in potential, delta G naught, and the current state of the reaction, which is Q. As the reaction runs, products build up, Q gets bigger, and that actually changes the value of the real delta G in real time. Whoa, so what does that mean? It means a reaction isn't actually trying to run to 100% completion. Its goal isn't to turn every last reactant molecule into product. No, its real goal is to reach a very specific balance point. And that target has a name, equilibrium, which we represent with a capital K. For any given reaction, K is a specific, constant ratio of products to reactants that the system is trying to achieve. So if Q is where we are right now, K is the destination the reaction is actually driving towards. And the logic is just so elegant. If your current ratio, Q, is less than the target ratio, K, the reaction says, gotta make more product, and moves forward. If somehow you have too much product and Q is bigger than K, the reaction will actually run in reverse to get back to the target. And what happens when Q finally equals K? The system says, we're here. It's reached its balance. The net reaction stops. And here's how it all connects. That initial blueprint, the delta G naught, is what determines the value of K in the first place. A reaction that's super favorable on paper with a very negative delta G naught is going to have a huge K value. Its target is way over on the product side. A reaction that's unfavorable on paper will have a tiny K. So let's put it all together. The real reason a reaction stops is because its current state, its Q, has finally reached its target balance point, its K. At that exact moment, the real-time energy change, the actual delta G, becomes zero. The downhill slope has flattened out, the system has found its happy place, and it stops trying to change. And this, right here, is the most powerful takeaway. It means favorability isn't some fixed, absolute thing. You can take a reaction that is favorable on paper and stop it cold just by letting the products pile up. Even crazier, you can take a reaction that's unfavorable on paper and actually make it go forward by constantly removing the products as they form, keeping Qs super small. You can manipulate reality. So, you see, chemical change isn't a simple one-way street dictated by some pre-written destiny. It's a dynamic, ongoing negotiation between its potential and its present reality. And if that's true for chemicals in a flask, it really makes you wonder, doesn't it? What does that say about the potential for change everywhere else in our world?